Why does the light tell you that there might be life?
So the light is a cosmic traveler, and the great thing about it is it's actually encoded information in it. That's how astronomers know how the universe works. This cool wonder that we hear, and then we can actually figure out the secrets of the stars, right? We can do that. Like kids seeing exhibitions for the first time. Look at the stars anew.
The wonder and the majesty of it all. This is StarTalk. Neil deGrasse Tyson here, your personal astrophysicist. I got with me as today's co-host, Matt Kirshen. Matt!
Hey!
And I have you in person.
I know. It's been so long since I saw you not through a screen. Yeah, look, it's real. You can put Post-it notes on my actual face rather than just covering it on the screen like normal.
Is that what I do?
I imagine.
Well, welcome to town. Welcome to my office here.
It's lovely to be back.
At the Hayden Planetarium of the American Museum of Natural History.
I mean, that's always exciting. It's fun to come to work. Does it get old? I hope it doesn't ever get old. The fact that you walk through the Natural History Museum to get to work.
It never gets old when I pass little children seeing exhibits for the first time. And I just remember when I was a kid.
The awe.
With that same experience.
Yeah, the natural wonder.
Plus, if you come through at night.
Yeah.
Don't tell anybody. But all the animals come to life.
I've heard the rumors. I've heard the rumors.
It's really true. So today is going to be a Cosmic Queries.
Great.
And it's on, I think, everybody's favorite subject. The search for life in the universe. Now, most people just talk about it, but some people have invested research time trying to figure this out.
Some people have actual expertise in it rather than just...
Maybe that's what I'm actually saying here.
Rather than people like me just, looking up at night and going, it's got to be something, right?
So I have with me Lisa Kaltenegger. Did I say that your name correctly? Kaltenegger.
Perfect. And it's so much fun to be here. And Neil, I have to tell you, even so it's the small kids that do the wonder when I walk through those doors, I'm back as being the small kid and just like...
You're a kid again.
And I do want to know if at night the dinosaurs come alive, because I'm here. We're just going to record until night because I want to see that.
You don't want to leave. You don't want to leave.
No way.
So I have your brilliant background here. First, you're an astrophysicist, but more importantly, you're an astrobiologist. So there's a whole bio side of you. And any biology I know, it's like, I had to pick it up on the side. But here is Centerline with you. And you're associate professor of astronomy at Cornell University. Who else was at Cornell? Somebody else?
I don't know. Was there anyone?
It rhymes with Fagin.
Is Reagan?
Let me just
someone involved in some communication as well as research. Someone, anyone who wrote books and.
There's this cool office on the third floor where Mrs. Kaltenegger is sitting right now, but it was the office that rhymed with Fagin.
Oh, so it's who got Carl Sagan's office? There's an answer to that.
Me.
Wow. So I was...
No pressure.
I was in that office 50 years ago.
Wow.
49 years ago, I was in that office.
You know what? If you come back and be in that office, just think about what's going to happen then.
Oh.
What
kind of sorcery will you be? So what you have to do is get your office set so that we can reprise what he did. Okay, I'm in his office, and he reached back, did a no-look reach behind him. No-look reach, pulled out a book that was one of the books he wrote, and then handed it to me, signed it to me. So you got to have all the books that you wrote on that shelf.
And then my shelves are like all hickory, like I have like books piles. So I'm going to just pull one and then the whole thing's going to come towards you.
Yeah, I feel like if I tried that, I'd somehow pull the bookshelf onto me.
You are director of the Carl Sagan Institute.
Absolutely.
And like I said, the answer to the question, who got Carl Sagan's office? And your research interests, you model habitable worlds.
And so the great thing right now is we know of more than 5,600 worlds around other stars, other suns, if you want. Of course, their name is not sun, but it's cool when you look up and you know that around every fifth one, there's a planet that's at the right distance, so not too hot and not too cold, and a rock, so small enough. And so it could potentially be a habitat, as you said. And so we live in this time where with the James Webb Space Telescope, big telescope we put into space, for the first time we can catch enough light to figure it out.
So why does the light tell you that there might be life?
So the light is a cosmic traveler, and the great thing about it is it's actually encoded information in it. That's how astronomers know how the universe works.
Yes, we don't know anything without that, right?
That's very true if it's dark.
You can't go there. You can't put it in a petri dish.
Even so, I do have to say the engineers should do a bit more work, right? I've seen this on Star Trek and Star
Engineers
Wars.
do
Like, they can
enough
do
for
it.
us. Now she wants them to go to the stars as well.
You heard it here first. Engineers, you're all lazy. Every
lazy
engineer.
I'm just saying, abandon the other stuff, all pulled together and make me an enterprise, right? I would like to go to these
Starship
cool stars
Enterprise.
we found.
Okay.
Do you want to upset this fine scientist? Engineers?
Can't satisfy us at all. Okay.
But you know what the thing is? Like, I'm even doing the blinky eyes. If somebody gets me Starship Enterprise, I will do that. I can do that.
Yeah.
If that's what it takes.
All right. All right. So in the light is what's encoded there that is of value to you?
So basically, when you have light, what we do as astronomers is called spectroscopy. We split it up in its colors, and we figure out if all the energy gets to us or if some of the energy hit the molecular atom before it got to me. And thus, even so I can set foot, I cannot set foot on these planets yet. I can actually figure out what's in the air of these other worlds.
Okay. So because each molecule has its own characteristic absorbing pattern, right? Yeah, okay.
Exactly. It's like a barcode. And if you think back to high school, like each chemical has a different structure. Like water, H2O, right, has an oxygen atom and two hydrogen ones. So it looks a little bit like a triangle, nearly. And oxygen, two oxygen atoms, looks different. So the energy that needs to hit it to make it swing and rotate needs to be different. And light carries energy, so which one's missing tells me, like a stamp and a passport, what chemical is in the air of this other world without me being able to get there, what's kind of nearly as cool as Star Trek.
So what are you specifically looking for? What things are you hoping to find or expecting to find?
So what we're looking for is when you look at the Earth and try to figure out if there's life on the Earth, the combination of oxygen and a reducing gas like methane tells you that something is producing oxygen and methane in huge amounts.
So reducing means you take an oxygen away from where it once was.
Exactly.
Okay.
Reducing basically means it reacts with oxygen and it will
steals
make it steals it. Absolutely. It's a good stealer. And so it'll make CO2 and water. So if you see it together in the atmosphere of a planet, you need two sources that produce it. And for methane, could be life, but also could be volcanoes.
What you're saying is that the methane and the oxygen, when left alone, are unstable and they will disappear unless somebody's cranking it out continually.
Or something is cracking it out.
Exactly. Just love each other. Think about this. They love each other so much that they will actually dance and go and make CO2 and water. So by them being together in the atmosphere, you can actually figure out that that's a fingerprint of life as we know it.
Oh, because if it still exists, if it isn't disappearing, and you don't have a volcano that's causing it.
So for the methane, the volcano could do it. But for the oxygen with the methane, the oxygen needs life to do it in those big quantities. But if it's just oxygen, it's not enough, because you could think about the long time. Like our planet's been around for 4.55 billion years, right? So if you had one oxygen ever so often, let's say one oxygen atom a week, then it would build up. So you need the methane to grab
Did
it.
you say one per week?
If you had one or one per month, you have 4.5 billion
you got
years,
a lot.
right?
You
It's
can
just
accumulate
like
it.
you can accumulate
Okay,
it. This is why you need the methane. This is why it's key to have the reducing gas. Other than that, it could just build up and you wouldn't know where it comes from.
Did you put all that in your book?
I did.
Alien Earths, the new science of planet hunting in the cosmos. Ooh.
And so the cool thing that when I think about these alien worlds, like some of them could be like ours, so they could be habitats, as we just talked about.
Hence Alien Earths, not just alien
Earths.
aliens.
No, and there's an S at the end, because the other way is also think about it that way. When you look at our own planet through time, you wouldn't be able to say you on the Earth if you were a time traveler. So that doesn't work like Einstein showed. We can go back in time. But if you could, you would not be able to figure out it's the Earth, and probably not, Statue of Liberty hands sticking out or something to tell you.
Wait, the Statue of Liberty shows up in every science fiction movie.
I know.
So you know it'll be there.
Yeah, so what
Or
would be their
TARDIS.
equivalent on other planets? Is this one of the things that you research? Like, if they don't have the same kind of like hominid shape to their bodies, like their Statue of Liberty would look weird to us.
I do
It
have
would look normal to them, but
It could be like lobster with a claw
but
sticking
still
out.
holding a torch.
A claw holding a torch.
Yeah, exactly. I figure it would still have a torch and a crown, but like it would be maybe 2 crowns.
That's
If it's
good
got
how
depends on how
biased
many
we
heads
are.
it has and how many.
But I think the good thing is, like, think about it, it might be easier to spot if it's like 3 legs or 5 legs. Right?
Yeah.
We only have 1 arm. Like, how did they do it?
One
like,
other
this one arm
right.
stuck out.
Wait. So, Lisa, how biased are you? How biased are we?
I think we as scientists, and Neil, you also were thinking about life in the universe at one point, right? So I think we biased, but in a good way, because we have to be ultra conservative to tell you that we found life. We don't want to just make it up. And so what we do is we look for something that we cannot explain other than with life, and keep our eyes open for things that are interesting, weird, and unexplained in terms of chemical makeup of a planet, or some kind of features like art, space art that blocks out some part of the starlight. So lots of ideas are coming in, but we have to be conservative to find it for sure. And then we have to have an open mind for something we don't know what to expect yet.
And this is all because we can't actually see the surface of the planet to see if there's cities or people or whatever. So you got to do this secondary way to get in on there.
Absolutely. But what's really cool is the next generation of telescopes that we're planning right now, the Habitable World Observer, for example, is supposed to be really big so that you actually can block out the star's light, see the tiny, tiny planet next to it, and catch the light from the surface. And thus, you know that you said about the biology in my name, right? In my professional description, I actually have a biolab, where we grow life in all the different colors from all the different parts of the world, like deserts, like ice fields.
Did she just say she creates life in her biolab?
She grows it. She grows it. I'm not. No.
I'm just verifying.
I mean, you've never seen my kitchen, but we've been growing life there for a while as well. It's I'm not proud of it.
At the
but
bottom
there's-
shelf of the refrigerator.
Yeah.
Okay.
There's some different colors.
Right.
all
Matt.
different.
So if you
I don't
have
know
any
what, like,
colorful ones, send them our way.
all
you
right,
know?
I'll chuck. Give me an address. Give me a mailing address. Can I ask you if someone like your equivalent on a different planet on a different star had a telescope pointing at Earth, what would be the markers of life that they would see from us?
That's exactly the question I had about 2 years ago. And with an amazing person here at the American Museum of Natural History, Jackie Faharty, we actually went to figure that out because we know where the stars are. There's an amazing mission called Gaia that's up there right now that is having a look where all the stars around us are. And we're like, where would we be the aliens? And so we figured out that if you just have our level of technology, that means you need to have the planet go in front of the hot star. So you see the star ever so slightly being less bright. For the Earth, that would be once a year for 12.8 hours. Then they are within 300 light years. So light from there to us and the other way around, about 300 years. There are 2,000 star systems where we could be the alien and people could be wondering, hopefully they're not bad aliens there.
We're pretty bad aliens. I think
They won't think there's life here unless they can see the Statue of Liberty sticking
Right,
sticking out of something.
I'm
sending it out.
strongly hoping that they also figured out that the gas combination will work because that lets you say that there's life on our planet for about 2 billion years. And that's how I got started in the field because I was part of the design team to build such a telescope to try to find other life on other worlds. And we were looking for 21% oxygen that's right now, modern Earth. And I was like, but the Earth's changed, right?
Right.
And then people said like, well, yeah, if you think that's important to figure out, do it yourself. And I was like very young and naive. I was like, oh, you can do this. Then I figured out how hard it was to do, so nobody had done it before. And this is why we figured out it was 2 billion years. And 4.55 billion years of history on the Earth. But for half of it, think about it, with a 24-hour clock, since lunchtime, you can actually spot signs of life on the Earth. And so in a way, the news is out of the bag if they just figured out our level of intelligence. And I'm having high hopes that there's more out there than just
That
our
assumes
level.
we are intelligent at all.
Exactly.
But
We
let me lay some
redefine it.
physics on what you just said. I think technically, if you want to be physics precise, it's not that methane and oxygen are signs of life. It's that methane and oxygen are signs of something out of equilibrium. And life itself is out of equilibrium. Maybe we need to be more creative about other things that could be out of equilibrium other than life. Is anyone thinking that way?
what's really fascinating, and that was where like in 65, they started out with this combination of oxygen and methane, right? So it's like old school science.
65, I mean
1965.
Gotcha,
Sorry,
gotcha.
1965.
Right. That's the Miller-Urey experiment.
Went around that time too.
Yes.
But the idea was then they said, well, it's just disequilibrium. But then we actually figured out that geology is super good in making disequilibrium. And sometimes life actually brings an atmosphere chemistry back to equilibrium. So there's only some very specific pair of gases that in disequilibrium would actually only be explainable by life.
Whoa.
And so that's like new, right? Because you'd say like, okay, 1965, they figured it out, right? We've done stuff since then,
Right.
even though we haven't found life yet. But it's fascinating. This search tells us so much more about our planet too and how it works
Yeah.
and how life works.
So before we go to Q&A, because this is a Cosmic Queries, one question before we hand it over to you, Matt.
I'm in. I'm ready.
You collected the questions from our Patreon members.
This is unsurprisingly, this may not be a shock, but this was one that brought in a lot of questions. So I'm going to try and get through as many as I can.
Of course
but
it would. Why wouldn't
This was a biggie.
I'm excited.
Okay, so let me just ask, what is life?
Ooh, such a good question, and a whole chapter in the book,
I
and
saw
no
that.
answer.
Is a blank page just after the what is life
Just a
question?
shrug. It's just a picture of
Yeah,
shoulders
it's
going
just
up.
you shrugging, yes?
It's really, really great because as an astronomer, I actually don't need to know what the basic tiny definition of what life is, because I need a biosphere that changes my whole planet for it to spot it somewhere else around another star. So in a way, I've put all the knowledge we have together, that it basically can evolve, that is Darwin evolution, that it has information content, and so on and so forth. And that's an entity that's encapsulated. So I put everything together from biology Nobel Prize winners and other people I talked to. That one I didn't talk to. I actually read his book. But I talked to the other people who do biology in the Carl Sagan Institute. And they're like, yes, no, yes. So I
That's
distilled.
a good sign. It means it's a vibrant field.
It's a vibrant field. So I distilled everything I know. And then I did put a blank page for your work here.
Did you? Oh my gosh. We were just joking.
Yeah.
Is that right?
I'm going to be honest with you. I don't think my version of my work here is going to be much help to the field, but some other people might.
You never know.
Some other readers of your book might take that baton and run further than I can. I think mine's more likely to be a shopping list.
Right, here we go.
And the first page is pretty cool too because it has alien wannabes.
Oh, yeah. Life on Earth that would
If you would show it to me, right, without DNA testing, I would be like, oh my God.
And of course, here is the tardigrade.
Oh, yeah.
Stuff on Earth that looks alien, basically,
Absolutely.
what that is.
And that survives things that it you don't know why it survives. We know it's desiccation for the tardigrades, but if you would sell it as like an alien, you'd get pretty far until...
Desiccation means you remove the water.
You remove the
and
water.
leave it for dead.
Yes.
And it's just doesn't care.
And it still
100
has the
years
ability
after.
to
So here's the page where you draw on your own planets and life and things.
I gave you a couple of planets, but you can do
starter
all
planets.
your
Very
your
nice.
own ideas here.
Very thoughtful.
See, this is what I want in a science book. I want facts and information, but I also want doodling
a
space.
couple
Exactly,
of
me
cartoon
too.
doodles.
Yeah.
And the really great thing is, like, when you write your own book, you can do what you want to a certain extent if
To
you
a
can
degree.
sell it.
That's right. So Matt, bring it on.
Given that you've just brought up sea creatures and other creatures on Earth that look alien, Craig Caldwell from the UK, from my home planet, says...
Wait, it's my whole planet too.
Oh.
The UK is not a planet unto itself.
I was there last week.
I mean, we have an ego. We have
You
an
might
ego
think
there.
that,
Yeah.
but not in New York City are you going to get away with saying that. Okay, go on.
So Craig asks, how possible is it that life has landed on Earth from a meteorite and has just become another animal? And he says, I'm pointing at the octopus here, but not exclusively.
Oh, I'd love that.
Love the show.
Octopus don't look like nothing else on Earth.
And I've seen them land in the movie Arrival, so they kind of look octopus-like.
Octopusy, right.
But the cool thing about this, if you think about where they could come from, and people think about Mars or other planets, actually the Earth had the best bet so far because it had watered the longest on a rocky surface. So the question is more like, if we were to find life on Mars, maybe we're going to find out they're actually Earthlings that became Marslings. But of course, it sounds cooler if we might be Marslings or some other things would
Did
be.
you say the word Marslings?
Well, I did hypothesize.
Didn't we invent a word for that already? Like Martian? There's a movie called Martian.
I know.
Nobody
but
calls Matt Damon Marsling.
Well,
But-
that's why you're the scientoid.
This is a key thing that we haven't found life on Mars, so I can't say Martian, so I say Marsling, just as a hypothesis.
Okay.
But the cool thing is, like, if there were kind of different life, we would find out if we do our sciencey thing, where we basically check everything and see if the DNA is made out of exactly like everybody else's DNA, chemistry-wise, right? Then you don't get away with calling it aliens, because for an alien creature, you'd hope that at least one chemical pair is going to be different to tell us.
Right.
Because it seems quite unlikely that even if life's on another world, what I hope, that it is exactly the same chemistry it will use.
Why is that unlikely when, if you talk to geologists, they see that similar minerals on other planets?
Absolutely.
Why did they get to have the same rock formation process, but you are not going to recognize that maybe biology is universal?
I think biology is universal. I didn't want to say that. What I mean is, like, carbon scaffolding and water are probably really, really good basis for life. But what nuclear pairs you could have taken for the DNA, you have so many options, or for proteins.
And there aren't so many options to make minerals. Oh, gotcha.
And so I think this is why, because it's going to be so weird when, for example, we'd find it on Mars, right? Would it have been a hitchhiker we brought if it looked exactly like the Earth? Or is it life doing the exact same thing under different environments down to the tiniest atom?
I bet everyone would bet on the hitchhiker.
Well, this is why we're going to the icy moons and hopefully just fly through the plumes
icy moons of Jupiter.
of Jupiter and Saturn, so that we don't contaminate those
And this is
pristine
why it's
environments.
whole departments of NASA whose job it is to make sure we don't do that contamination, right?
Exactly, it's a job, but it's so hard to do because life is very hard to kill. Good thing. It's a good thing. It's a good thing.
Yeah,
She
you should
sounds
say that with like a.
She's tried it. I've tried to kill it. It's so
That's
frustrating.
You should see,
Superman.
I've got so many hammers. We've tried fire. There's nothing. That's what she does most of the time in her lab.
But the coolest thing is, actually, if you think about life on the Earth, you would actually have to melt our planet to about 10 kilometers down to actually eliminate life, because there's life down to about 10 kilometers. That deep. And so if you just
She's thought about how to
sterilize,
get rid of life on Earth. This worries me. Matt, does it worry you, Matt?
How do we autoclave Earth?
Here's how you get rid of life on Earth. Melt it down to 10 kilometers.
Because we know we now know there are these extremophiles, right, that can survive in like volcanic
or
gases.
tardigrades, right? Yeah.
So you can't just sort of you can't just boil Earth for 2 minutes.
I think about it as more hopeful, because even if we were stupid enough, and I hope we're not, to actually destroy all of ourselves, destroying life is luckily so much harder that some other kind of bug might actually make it to the stars if we can.
Plus, if you look at the extinction episode record, maybe we should be amazed we're all still here. There's a 90% extinction episode, the PT extinction, Permian Triassic, and then there's the famous one, the KT extinction. We lost 70% of species. I mean, the universe has been trying to kill life on Earth like for years.
And that here we are doing a podcast. It's just
I really
a few million
think
years later.
this cool wonder that we hear, and then we can actually figure out the secrets of the stars, right? We can do that. I actually think we should give this much more wonder and credit, and thus, like kids seeing exhibitions for the first time, look at the stars anew. We figure out
The
what
wonder
they're
and
like.
the majesty of it all.
So Torsten Diekhoff from Berlin says it took evolution quite a while to develop multicellular life on Earth. How likely is it that most planets are populated only by bacteria or similarly simple life forms?
Also, great question. So this 2 billion years of oxygen and methane combination gives you a range of life. What we don't know is how fast evolution could be on another world, because we have only a sample of one, ours. But we think with more and more oxygen, you get more and more complex life. Just think dinosaurs. There was more oxygen in the air actually when the dinosaurs were around, thus big creatures. And so
But right now we're 20, 21%.
We're 21.
What was it back then?
we think 30 to 32. And so the coolest thing is, like, Jurassic Park worlds would actually be easier to spot than us. And so we published this, was pretty funny. And then the headlines were like, alien dinosaurs. I'm like, whoa, we didn't talk about alien dinosaurs.
You knew that
We
was coming.
just said-
You can't put those two words in a title and have the press properly interpret it.
But having said that, I saw it differently, because if we now get everybody who loves dinosaurs to also love exoplanets, they have to if we're looking for alien dinosaurs, right?
That gives us 100% of all kids.
And I think that's exactly what we need to get to the stars.
I feel like we're stealing them from the anthropologist and the paleontologist, but I'm okay with that.
Wouldn't they learn so much more if they had other dinosaurs on other planets?
Yes, they would.
See?
Yeah.
It's just like we're helping out.
Yeah. I mean, that is a way to get kids into science. Kids love space. Kids love dinosaurs.
Dinosaurs in
Exactly.
space. There it is.
And then if we tell them that you can go and talk to comedians and do funny things and be on the air and say, hi, Mom, right? You know, what else is there that they would want? Maybe it's superpowers.
Yeah.
But, you know, if you were on one of these other moons like Titan, because it has so much less gravity but a dense atmosphere, you could flap your wings and you could actually fly on Titan. You couldn't breathe, but you could fly.
Yeah, you'd suffocate. But other than that, everything's
Other than
fine.
that, right?
But
It'd
you
be
have
easy to fly, you're saying.
You'd have
Yes.
a great 60 seconds or so as you chokingly fly in a panic.
You could also come with a spacesuit. I'm not saying you can't do that.
Mm-hmm.
So what's the gravity on Titan then?
It's just much less than here.
Yeah.
Maybe it's a third. Moon is 1/6 Earth.
Yeah.
So it'll be no more than half.
Yeah.
For sure.
I think it's somewhere around a quarter, yeah.
Sure. What do you weigh here on Earth? Pounds, dude. This is America.
I have no clue about
120?
pounds.
120?
Yeah.
Yeah, so on the moon you'd weigh 20 pounds.
Just think about how
okay.
high you could jump, and thus we have all the kids back. We have superpowers we can give
Then they
them.
give
Yeah.
damn, you want to give them superpowers, dinosaurs, and space.
What more do you want?
Be kind to your fellow
Yeah.
scientists.
It does look fun bouncing around on the moon. I mean, that feels like...
The funny part is like when you see the astronauts skipping, right? That's what I show my students when I teach. I'm like, look, this is real life skills. If you ever find yourself on the moon, you know that you have to skip.
And skipping, kids stop skipping like in middle school. It's
Yeah,
like a
you shouldn't
loss.
do that because you might find yourself on the moon
You got
at
to do
one
it on
point.
the moon.
Yeah, do they have to have skipping classes in NASA in training?
I think they do. They do skip underwater.
Is it part of selection?
I don't know that. Neil, do you know that? Have you ever tried out for an astronaut?
No, the underwater is just for 0G, not for low G.
Right, but did you ever try out for the astronaut program and actually try to figure out if you had to skip?
No, I never did that. No.
I never did that either. So Matt, you have to go and become our token astronaut to figure that one out.
I mean, I think I'm still a good skipper. I think I can still
right.
skip to a decent level.
All right.
But you will have to do it for the ESA, right? The European Space Agency, who will have to figure out
Yeah.
about the American system.
Well, how does it work? Because I'm on my way to getting citizenship, so I might be able to.
Ooh, do
Can I
both.
straddle both? Can
U.S. citizenship.
I get the two patches?
Okay. Why not?
Why
Yeah.
not?
Dual
Yeah.
citizenship. Go for it.
Science is international, so that must
Invite
work
us to
too.
the launch. Yes.
All right, it's a deal. You heard it here first. So there's a couple of questions about different types of life form and different environments. So Victor Ray Rutledge from Texas says, can there be entities, say life forms, which exist outside of any planetary boundaries? And then John O from Iowa also says, what are the extremes of environmental conditions that we think life could exist in and we look for across the galaxy?
I'd like that. So that would include planetary moons, maybe asteroids, comets, or just free floating in space. Are these legit places?
I think it's really great. So the first ones are absolutely legit places. So there's no reason a moon couldn't be a habitat. Or maybe even an asteroid, even though there becomes a bit tricky because it gets really cold. So you have to dig down deep. And in a moon and a planet, you have residual heat from being actually formed. So you could do that.
Well, wait. So the moon doesn't have heat left over from being formed, but Earth
No.
does, right?
Right. Earth does. Sorry. So if you have
Right.
moon,
That's all they
or-
heat down under, like the mid-ocean ridge and all of these places.
Exactly. And the other moons in our solar system around the giant planets, they are actually being molded. So the other moons actually tug on them as well as Jupiter, or in the other system, Saturn. And so there's tidal heat that gets generated. So they actually get warm. And this is why we have oceans.
We have tides on Earth that move in and out, and we credit the sun and moon for that. So you're saying we have tides on moons of Jupiter. And what effect does that have on the...
Absolutely. So we have tides and moons of Jupiter. And so what it does is basically we have these ice balls because it's so far away from
Right?
the
It's
sun.
outside the Goldilocks
It's
zone.
outside of the Goldilocks zone, but because of this pulling and pushing that actually deforms those moons, there's heat that melts the ice under the ice shell on top. And so we know those ice shells are actually swimming in liquid oceans. And so this is where we have high hopes that maybe those oceans could also have kind of life. And so this is what it can do
No
for you on
shortage
the
of life
moon.
in our oceans.
No.
So that's a sensible thought.
But it's a very different ocean. So this is why we're sending things there
why
to
is it
investigate. Oh, because it's much smaller and it gets like bent out of shape. And hopefully the bent out of shape has been since forever. But for some of the moons, they are a little bit smaller, like Enceladus that goes around Saturn. And so it's a very not so deep ocean, but we think it has been around for millions of years. But the question is, has it been around for billions of years? And how long do you need an ocean to get life? And so I completely hijacked that question. So yes, life actually has some boundaries, as we know. It's when you destroy the cell walls and when you make it so hot or irradiate it so much that everything breaks down the structure that basically lets you concentrate chemistry in the inner part of a cell.
I like the way you're
What do
saying
you
that.
need to do?
So I do know that molecules are held together by certain binding energy. And if exterior to the molecule, there's more energy than that available, just bust up the molecule.
Exactly. And it's
And we are complex molecules. So you don't want to get busted up.
You definitely don't want to get busted up. And it's actually even earlier because you need the cell walls because those allow you to get some chemistry in and some out. And so if you were swimming in a huge ocean, one of the key problems you have is to concentrate the chemistry enough to get something like DNA and RNA started because you need concentration for that.
Because you need the frequency of them bouncing into each other.
Exactly. And the ocean is vast. And if there's like a couple of molecules, when are they ever going to meet, right?
Right.
And the other thing is like when it gets too cold, we think these reactions are starting to be so slow that it might take so long for any of them to take place. So there are some limits on life, but so far we think you need, at least for starters, a rocky surface and some water where you can concentrate the chemistry and make these kind of vesicles that become cells. And then wherever you find those conditions, hopefully.
But one of those questions was, we went how many? 3.5 billion years with single-celled life? Is that somewhere around there, right?
Absolutely. And the key point is
That's a long time.
That's a very long time, but there's two good things. So there are stars that are older than us, and planets are as old as their stars. There's a star that's older, well, that was older than the Earth is now when the Earth formed, and it has planets. But also we have no idea what sets the evolutionary clock. And so it could be faster evolution or slower evolution
All I'm
in other
saying
worlds.
is, it seems to me, Lisa, that if Earth went 3.5 billion years with single-celled life, it could easily have gone another 3.5 billion years.
And this is why this lively discussion is so helpful in science, where people actually are now coming to the conclusion, or at least that's the best explanation we have right now, is that if you have enough energy available, and that was the oxygen content in our air, then you will make more and more complex life. And it's not completely done yet, but that's the best explanation we have for now. So get oxygen.
So if you sneak some oxygen in early enough, we might have had our explosion of complex life sooner in the timeline of the Earth.
That's basically what the biologists are telling me. And so at that point, because I'm an astrophysicist, even an astrobiology leaning one, my knowledge gets a little bit less complete. So I talk to people, but it kind of makes sense. If you had energy available that life could easily use, you could become more complex.
So the life becomes opportunistic.
Absolutely. Opportunistic is, I think, a great word for life as we know it.
Cool.
So there's a kind of related question about the environment from Kevin Vale from Chester, New Hampshire, who says, I've always wondered how massive of a rocky-type planet would carbon-based life still be possible? How much higher or low gravity might affect life?
Ooh.
And so that's a great question. So generally, gravity should mostly affect the structure. Let's assume everything's equal. You have a rocky solid surface and you have some water. So then gravity affects your structure. You need enough pressure on top of your ocean not to evaporate the whole thing, right? So you need that.
So chemically, what you're saying is, if there's just vacuum above the water, there'd be nothing to keep the water in its liquid state.
Exactly.
You need the pressure of the air in order to maintain that. Okay.
That
Completely
makes
right.
sense. My in-laws live in Colorado. It's high altitude. Water,
Trying to boil something.
yeah, water boils off pretty quickly. You
Yeah.
dry out very quickly.
Yeah, yep.
That's and that's a fraction of vacuum.
Right, yep.
Or you could have an ice layer, like in the icy moons, right? That basically keeps your water below protected. And so how small can you get? As small as you allow me to have liquid water on a rocky surface. And so those moons that get tidally heated, actually from the first principle, without the tidal heating, they would be too small because everything would be frozen and cold. But because they're tidally heated and physics works in the whole cosmos, you basically get this additional liquid water. So what's too small depends on the circumstances. Do you get pulled and pushed from your neighboring moons? Yes or no? And so we're still learning the limits. But at one point, when it becomes so incredibly big, when it forms, it will actually grab onto all the gas that's around it, and it will become one of these big planets like Jupiter or Saturn. And so at that point, we don't know how you could have liquid water with a rock interface, where it's not supercritical liquid water because there's so much pressure on it and so hot.
So you make an interesting point. So the more massive the planet, the more likely it would have retained gases that in Earth's history or Venus's history or Mars's history would have been long lost into space.
Absolutely. So when we think about this, really, it's like, why does the planet have an atmosphere? And it's not the whole story. Then it's really the pull of gravity that the planet has versus the escape velocity, how fast you need to
Of
be
the molecules of the air.
the molecules in the air.
So there's no such thing as a jumbo rocky planet
We
with
don't-
only rocks.
We don't think so.
Okay.
And so that's the really interesting thing, again, with the James Webb Space Telescope, because what we found, most of the planets, I said thousands of planets, right? 1 out of 5, maybe like ours, 200 billion stars in our galaxy alone. Billions and billions of possibilities, even so, of course, he never said it. But what's really interesting here is that the most common planets are some we don't have. They are bigger than the Earth and smaller than Neptune. So these super Earths, great name, whether they're better is absolutely not clear. How are they like? This is what we're now figuring out. We don't know from first principles. We have some ideas, but the James Webb Space Telescope lets us look and confirm those.
Now, you did say billions and billions. The man wrote a book called Billions and Billions.
I know, after everybody
After,
kept saying
yeah,
it.
after
And then
everybody.
he went onto the show, right, and said, okay, now I say it officially. And so,
Do you know who first said billions and billions?
who did?
It was Johnny Carson.
Johnny Carson, right?
From The Tonight Show.
But he basically interpreted it as saying that Sagan said it, right?
Yeah, he was imitating Carl Sagan in an exaggerated way.
Yep.
He knew he said billions.
I love
And he said it so in a fun way. You got to double up on it. Billions and billions. Plus, there was a cartoon where it was like Carl Sagan as a child. He says, "Look at all the stars. There must be hundreds and hundreds of them."
Perfect. It's part of pop culture.
You got it. In 1976, Carl Sagan published a paper with Ed Salpeter speculating on life in Jupiter's atmosphere. Until now, you've only been talking about rocky surfaces. And he was imagining predator-prey, a combination of life forms that could sustain themselves without any care at all about the surface of anything, like balloons that had buoyancy, these flying creatures living off the temperature gradients within the atmosphere. Is there much thought still given to that idea?
I love that paper just because it shows the creativity that you need at the edge of the forefront of science. But we have learned more and more about the origin of life since then. Luckily, science always learns.
It was 50 years ago.
It was 50 years ago, and it was a visionary paper. But what we've learned so far is that you need a rocky surface and some kind of water to get this chemistry
start it.
going, to start it.
Start it.
But
you
maybe
can't just have molecules come
Floating
together
around.
and convecting air cells.
the chances that they're going to stick to each other and make a kind of cell are just so small, even if you give it 4.5 billion years. But having said that, once we have such floaty things, we could always bring them to Jupiter and reenact Carl Sagan and Salpeter's amazing paper.
That'll be our atmospheric zoo. Wow.
There's some kid watching that. That's your task. That's your 50 years from now. That's going to be your job.
That sounds great. I want to be a zookeeper there too.
So what else you got?
Well, we've been dancing around this question and this idea a little bit, so let's just ask it directly. This is from Gavin Traber from Sacramento, soon to be Dr. Gavin Traber,
Ooh,
RNA
Congratulations.
biochemistry and molecular medicine.
Ooh, go for it.
And Gavin wants to know, do you think the origins of human life on Earth, or at least the basic building blocks such as amino acids, came from the stars already formed from elsewhere, or were they originally synthesized in a prebiotic Earth?
So let me offer a version of that question back at you. Okay? You guys always talk the talk when the amino acids are discovered on meteorites being delivered from space. You talk the talk. Okay? But Earth is made of all these same ingredients. Why do we need any ingredients from space at all if the birth ingredients of Earth has all of those ingredients all by itself?
I really really think it's more the glamour from everything that comes from space. Because you can make the chemistry down here too, but it's kind of cool to find it on an asteroid or a meteorite or another moon, right?
It's got a cool factor.
I think it has a coolness
Is there
factor.
even any way to necessarily know?
Which one's which?
Yeah, like how would we know whether this amino acid that became...
At that point, we need the TARDIS. You, me, and Neil have to go in and then get back
TARDIS,
to
as
that
in
point.
Doctor
In TARDIS
Who's.
and Doctor Who's
Yeah,
TARDIS.
yeah.
Get
The
point,
doctors.
not just to the right time, but to the right location. This is why I want the TARDIS, right? Because it gets you to where and when you want to be.
Space and time.
And figure out how life started here on the Earth. Then we could tell.
I think I know the answer to this, though.
Go ahead.
I think. Many amino acids have a chirality to them, where they are different in a mirror from what they are in real life. So there's a certain configuration of the atoms that is just not symmetric in a mirror.
Am I right in thinking that one way is good and the other way is evil?
One has a goatee.
That's how we tell. That's how you tell.
That's how you know.
One way is good and the other one is just blah. Like one is your favorite food
Mundane.
and the other one is blah.
So the amino acids that would have chirality on meteorites are 50-50, and all the ones on Earth are they left-handed or whatever is the handedness. So all life has only one-handedness, but the ones from the meteorites have both.
Exactly. So, but the key point is that did you need to bring them to the Earth so life had enough to eat? So the theory would go that, if we're starting out and we didn't have life yet, we probably had 50-50. And it's quite interesting that there are some researchers who say that it could have gone either way.
Yeah.
But life just picked one. And that's the one it picked. And what's really fascinating too is that when we're trying to make life in the lab, and we can't do that yet, that's the problem, right? We don't know how life started because we can't do it in the lab. And so to all the amazing colleagues, because before that you said, I don't like engineers. I love engineers, married to one. But basically just to say, it is really hard to make life in the lab. And what you would want to do is you would want to make it with a different chirality. So you're making it from scratch. And that's so hard to do. But
and then when the
trying
life
to do it.
escapes the lab, you
know
can
which
track.
ones to kill.
We know which ones to kill.
It's not going to kill you because you are blah, right? It doesn't want to eat you.
You're not interested. It can't digest you.
Exactly.
Right?
It's a safety measure.
But I bet if it's chasing you down the street, it won't know until after it's in your stomach that it couldn't digest you.
That's evolution, and we have like billions of people, so hopefully just don't be the one that it eats first.
First, right. So we have time for like one more. Matt, what do
Okay,
you
well,
have?
I like this question from Eduardo Labato from Spain, but living in Finland, but asking the question in English. And Eduardo says, does the discovery of dimethyl sulfide on planet K218b by the James Webb make us rethink how probable life is in other worlds? And also, what makes DMS a marker of life?
So what's really interesting, once
Let's back up for a minute.
Yeah,
So K2, that's one in the Kepler's catalog. Is that right?
K2, K2/18b.
Right. It's not like the other peak.
Yeah,
in
the other
Himalayas.
mountain. We've just discovered it. We've discovered life on that mountain. Yeah, it's a climber. It's
a dead climber who used to be alive. Right.
His name was Ben. He had feelings and family.
Oh no! Come on.
Okay. So
Can we survive?
That's its catalog ID. K2. Keep going.
18B.
18B. Okay. So now tell me about this molecule.
So basically it's DMS, dimethyl sulfur, and on the Earth, life makes it. But now we have these other planets, we were just saying these super Earths and mini Neptunes. We don't understand the geology, we don't understand the photochemistry. So even if we see gases that on the Earth in a chemistry like ours would actually indicate life, you have to be very careful not to misinterpret it. And that specific case is interesting because it tells us something new about these weird worlds we don't have in our solar system. We definitely try to think about ways that life could be there. But if you have so much gravity, you would have kind of a supercritical ocean under a huge amount of hydrogen. And on the Earth, the bacteria that makes DMS needs light. And so there it would actually be dark. And so absolutely, we're thinking about this a lot.
And you can deduce all of this from just the James Webb data.
From the spectroscopy, from basically looking at the light. And so what's really important about these discoveries that they
It
make
feels
us
almost
think.
voyeuristic, you know?
Yeah.
It's like, I'm spying on you.
Do these bacteria mind us? Like,
Well, this is the question, right? We haven't asked for the consent of spying on other potentially alien worlds, but we're doing it very kindly. No interaction. We're just looking.
Just
and
looking.
then
Just
if we
their
find something
spectroscopy.
interesting,
There's
you know,
still probably a law
that's.
against it, but that's right.
I was about to say, but we don't know the laws there, so
Oh,
it's
right.
not just the engineers; it's also the lawyers who have to get up to speed.
Right. So it's intriguing. This planet is bigger than Earth, but not as big as Neptune. Is that right?
So it's bigger than Earth, but not as big as Neptune. But the key point is it will be so different from the Earth that you shouldn't just go with the same conclusions when you find something that would indicate life on the Earth. And that's what we're learning. The more interesting planets we find, the more patterns we will see, and the more we'll learn about geology, photochemistry on these other worlds, what we just don't know because we never had one of those
If
in
it
our
were an
system.
Earth-like planet, then you'd feel more confident.
Oh my God, if it
asserting
were an
this.
Earth-like planet, I'd be so much more excited about it. But if you have a mini Neptune with a huge hydrogen atmosphere, no light hitting, a potential ocean, we don't even know if the ocean is there, then I'm just saying maybe intrigued, but not sold yet.
There it is.
I like that. Intrigued
that.
but not sold.
All right, we got to end on that note. That's a very hopeful note, I think.
I think the
It's
wonder,
a curiosity-stimulating note that you just ended on.
I think what's really great is that we live in this time where for the first time we could figure out if we're alone or not, and all of us get to live in it. So that wonder that we all bring to looking at the night sky,
Childlike wonder.
childlike wonder, we could point up, count to 5, say 1 out of 5 might have another Earth, but
1 out of 5 of the stars. Uh-huh.
might host another Earth. But maybe in a couple of years, we could say, oh, that one
Look there.
shows signs of life.
And then you realize that one's actually just a plane flying overhead.
That shows signs of life
It
too.
does have signs of life in
An
it.
Elon satellite that's going across, right. Oh my gosh, Lisa, thanks for coming to town.
Thanks so much for having me. This was fun.
And congratulations on the book, Alien Earths.
You know what? Somebody called Neil deGrasse Tyson said he was good. It's on the back cover.
Whoa!
Yeah. Who's that guy in that
Wait, let
blurb?
me see. Hang on. Let me just see what that says there.
Is that top blurb on the list?
Of course, top.
It's my duty, if I'm asked to blurb a book, to make the shortest blurb possible. It's still informative,
Yep.
and that usually ends up at the top. Lisa Kaltenegger's breezy narrative style invites you to experience with her the challenges and joys of being a scientist on the frontier of discovery. Who said that? Who said that right there?
It's some guy Neil deGrasse
deGrasse?
Tyson. Who is that guy?
Lisa, congratulations on the book. Thanks for coming through town.
Thanks so much for having me.
All right. And next time I come to your office, we have to reenact some Carl Sagan things.
Absolutely. I think it's going to be this year because it would have been Carl Sagan's 90th birthday. You should come. We should sit there and we both should think about what he'd want to do now.
All right. We'll work something out, I promise. And Matt, good to have you here in
Such
person.
a joy. Such a joy. Look at this. Look at this. Real.
Can I do that too?
Yeah, that's
Matt exists. He's not a bot in,
it's
in
it's
Los
real. I'm
Angeles.
not some avatar.
Yeah.
And he's very
Flesh
happy
and blood.
he's sat in the middle of us. So he could
Yeah,
get touch
that's what I came here for. I came here for the physical touch. We've been lacking it in recent
It's really
years.
a facial. That's how you should think about it.
Yeah.
A facial massage.
Massage, yeah.
And keep that podcast going.
Thank
Probably
you.
Science.
That's
Very
it.
good.
Yeah.
And I finally remembered it correctly.
You got it dead on.
Probably Science.
That's the
All
one.
right. All right. After this interview with Lisa Kaltenegger, I'm explicitly reminded, that the best scientists out there are those who are still kids. What does a kid do? They turn over rocks, look behind trees. They're curious about everything, because the whole world is a frontier to them, a frontier of exploration. If you carry that into adulthood, then the universe is there for you to reach out and explore, discover. And then you have to pick up some math along the way so that you can speak the same language that the universe does. But when you do, oh my gosh, What a joy it is to be a child again. Not many adults get to make that claim, but those adults on the frontier who are scientists do. That is a cosmic perspective. Until next time, StarTalk. Keep looking up.